into complementary series, and so on. So the idea is that one works in principal series and then makes an analytic continuation. For instance, if you are in 4D, the same R matrix can be, well, the R matrix written in this formalism can be generalized to describe more general representations. For instance, any spin. Okay, here you have the two SU2 spin L dot, which can be combined into a representation for SO4, and so on. So let's keep it simple so far. Now the thing is that, yeah, I think last time, since we finished with the Lagrangian of efficient theory and some remark about that, I wanted to say what can one compute now, or at least describe with integrability in this fishnet by scalar theory. So I'm quickly rewriting the Lagrangian of the theory, and I will investigate two types of correlation function in this theory. Right. So here we have two kinetic terms. No, I'm Euclidean. Too many deltas. Okay. All right. So let's consider this operator, which is so-called BMN vacuum and n equals to 4. This is protected operator by supersymmetry. The supersymmetry is broken because I was explaining at the end of last lecture that this theory is precisely obtained by a SU4, a twisting of the SU4, so a breaking of the SU4 symmetry of n equal to 4. There are symmetry of n equals to 4, and therefore all supersymmetry is broken. There are middle grounds where some supersymmetry is conserved, but in this specific fishnet limits, supersymmetry is broken, and this leaves constraint on the fact that this is a protected operator. And in fact, this type of operator is described in the planar limit, which is the framework we always work in, by a very simple, I mean, topologically simple set of Feynman integrals. Okay? If in this point I have insertion of J fields X, and in the other point J bar, the two-point function is nothing but a summation of diagrams of, is a summation over n, over this index n, of diagrams of this type, where n counts the number of wrappings. Okay, so you can see this as a square lattice wrapped on a cylinder, or a sphere with the two punctures. Okay, so J fields X propagate along the cylinder in radial direction in a sphere, and there are wrappings which are propagations of fields Y, okay, so that the vertices are X, Y, X bar, Y bar, and the number of these wrappings is reflected by n here. Okay, it's counted by the power of the coupling. So in this case, so in general here one has a number of wrapping n. Okay, let's say. So the idea is that the regularity of this lattice allows to express non-perturbatively a two-point function of this type via spin chain object. So you can notice here that it's the type of quantum corrections in this two-point function are very finite size objects, right? Because they are wrapping around the puncture. If the operator would be infinitely heavy or very heavy, this type of corrections would be observed at very large loop order, right? So, and this is the first observation. The second observation is that this resummation in wrapping can be mapped to an integrability problem, so to the spin chain I proposed last time, as follows. I'm setting here j equal to 3. Okay. Let's study j equal to 3. Okay. For j equal to 3, it is possible to define the transfer matrix that I wrote last time, which is a convolution of our matrices. Okay. Trace over an auxiliary space, infinite dimensional auxiliary space, R10, R20, R30. Okay. What does it mean in pictures? Here I will have a kernel, x1, y1, x2, y2, x3, y3. Each of these squares is that R matrix. Precisely. Yeah. So this is R10, R20, R30. These R matrices are convoluted in vertical direction, which is the auxiliary space, okay, auxiliary space and physical spaces, right? And I'm considering to have periodic boundary conditions. So these two little edges are these ones. Okay. Now it is the case that this transfer matrix is the transfer matrix of an integrable model, as I already argued last time, but what is interesting for us is that if I take the limit for u, the spectral parameter u in the definition there, okay, which tends to minus d over 4, and I set delta 1 and delta 2, so delta x and delta y, excuse me, equal d over 4, which means that I consider the case of isotropic theory. Isotropic, I mean that the propagators in both directions have the same scaling dimension. Okay. Well, in this limit, this kernel becomes or is rather proportional to another kernel. Well, this is the periodic boundary. Okay. So if I call this kernel, say, B operator of a length 3, now the two-point function, the entire perturbative expansion of the two-point function is essentially described by a geometric series in the operator B, right? Because adding one wrapping means multiplying by one more copy of the operator B. Okay? So what is even better to study, I would say, is the point split setup. Right. So you see that if you open up the two-point function into a 2j points function, then you can recover the two-point function, of course, taking the Euclidean OP, which identifies the points. Okay. So in general, you will have something like this. Okay. Right. Yeah, I think. Of course. Yeah, I need a little bit more space here. All right. Okay. So you have n powers of the operator, means to insert n wrappings that are then applied to a boundary object. So of course, the last of this column of lattice should also be added, the external propagator to complete the lattice structure, and then these external points y will be set to some coordinates. So this expression is a sort of quantum mechanical expression, spin chain-like expression for trace of x in x1, x in xj. Sorry, this is j. All right. Trace of x bar in x prime 1, x bar in x prime j. Okay. So one thing you may be disturbed about is the fact that I have elementary fields inside the same trace, which are located at different space-time points. But as I was explaining, there is no gauge field anymore in this theory. This is not a gauge theory, right? So, okay, these are not gauge invariant operators, but it's not an issue. After all, these are the same type of object that Simon was looking at, literally. If I would put j equal to 3, it would be, in 2D, it would be the same problem that Simon looked at. Maybe what is different is that I will set the values of delta not at the same value that he would choose. But that's it. So in order to compute this quantity, well, one simply resums the geometric series in the operator, finding in the graph building operator, finding something like that. Right? All right. So we have to compute this object, which means that if we know a basis of its eigenfunctions, essentially it is done. And let me show this in the case of j equal to 2. Why? Because j equal to 3, we just seen that it's not so easy to diagonalize. But j equal to 2 is very simple to diagonalize. Right? So now I showed you the example for j equal to 3 to be slightly more general, or any j. But I'm going to work out and say solve the problem for j equal to 2. Okay? So for j equal to 2, the advantage is that the eigenfunctions of B, okay, the eigenfunctions of B are fixed by the fact that the spin chain has conformal symmetry, that is, the transfer matrix or the B operator, they commute, they are invariant with respect to the diagonal action of the conformal group. And since these act only on two sides, well, a basis of eigenfunctions for B are the conformal triangles. So you think, if you're really not familiar with this, you can think about a system of two spins. two SU2 spins in certain irreducible representation, and then you have their tensor product. And their tensor product, you know that it can be decomposed over the total spin if the system has an Hamiltonian that is SU2 invariant, that is, it commutes with the total generation, the total generators of SU2, so the diagonal action of SU2. Okay. All right. And then you will have some intertuning vectors if you want. Depends how you want to call them, but we are all familiar with this basis, right? So you have the first two representation, the third representation, and the magnetic momentum in the total spin. The same thing we can do here, because if you have only two sides, it's like having two spins. Okay. So now these are the two spins, x1 and x2, that evolve in this direction. And the evolution is given by iterative action of B. And so there will be now a product of two representations, irreducible unitary representation of the principal series, that it is known they are also decomposed as a sum over irreducible representation of the principal series. Okay? So delta here is d over 2 plus I nu, and I'm specifying also L because I also need for completeness in order to span the space-time, to have a complete basis. L is an integer, which is the rank of this symmetric traceless tensor. Right? So this is what you would usually look for even in a conformal partial wave decomposition. Right? So we are it's like exchanging in an S channel. This is like S channel. Symmetric traceless tensors. Symmetric traceless primaries. Yeah. So conformal symmetry constrains the eigenfunction of the problem, which are the, say, well-known conformal triangles. Okay. So there are different ways to express them, but say.
So here you don't take advantage of integrability, you only use conformal symmetry.
Yes. The integrability problem can be formulated, and as it was explained before, requires some effort to be solved. Sure. But since I want to do this on Blackboard without Mathematica, I will do the case of two sides where I already know the solution. Because I'm going to look now rather at, I want to comment rather on some aspects as a conformal field theory at this point. So I just want to look at some data. Okay. Yeah, the effect of this is more destructive than that. I think it's over. All right. If you apply the usual formula of the conformal triangle, where the powers are fixed by the scaling with respect to the 3 points, having fixed delta x and delta y to d over 4, these are the powers you will find. And here L is encoded in a numerator that multiplies the triangle, which can be expressed in a number of ways. my favorite way is with the Pauli matrices. But let's say maybe more canonically is, I mean, more friendly to any dimension would be this, where n is null. Right? So this generates a symmetric n traces vector thanks to the condition of n to be null. And if you are curious to know why I speak about Pauli matrices as well. This would be a basis of null vectors using spinors, so it's very convenient for computations. In any case, the thing is that, right, this is a basis. One can compute the eigenvalue easily. How? We start triangle again.
Sorry, why is there a log? So, like, if L is equal to 0, you get a log? Or you cannot have L equal to 0?
Right. Sorry. Yeah, sorry, I think I have to put the L, yes, outside.
I guess L also enters in the power of the propagators, no? Like delta minus L.
Yeah, I wanted to give it in terms of Pauli matrices where I can already normalize the numerator, because it's nice, because it disturbs to me to see something, because it's not part of really of the scaling power of this propagator. But you are right. Here I have to set minus L over 2, minus L over 2.
But this is supposed to be just the kind of conformal 3-point function, right?
Yes.
In the end. Okay.
Sorry, just another step.
Sorry, is there a liquid to clean this? Because I cannot proceed otherwise. I'm afraid that every time I will cancel a formula, I will not be able to. They are both very dirty. Very good. Okay, I'll try.
But just one stuff. Are you regularizing the theory in some way to make it conformal, or?
That's for the afternoon.
Okay.
The only thing I can say you in this regard is that, yeah, I claim that it is a conformal theory, but I didn't argue that, and I'm not going to argue in full details, but look at mass generation and renormalization of the coupling in that Lagrangian. So we have trace xy, x bar, y bar. This is the vertex, right? So now take it as a 4-point function and compute its quantum corrections. It's a single trace, right? So it starts with this. I'm using the formalism of ribbon graphs with the 2 indices, right? Just because I want to check planarity. So this is a single trace, and it is planar. We agree with that, okay? It's just the vertex of the theory. And then, if I continue expanding, I will have this. Okay, because now I have 2 vertices, and I cannot have this. I cannot have the same Feynman diagram as an integral, but with this structure of SUN indices, because this vertex would not be allowed. Look, xy, x bar, y bar. This is the vertex of the theory. But then here you would have yx. You can never have y and then x, because you don't have this vertex in the theory. Right? So this is not allowed. But this is allowed, because I'm intertwining, I'm exchanging the two legs. But it clearly adds a genus to the surface. So if I start to count the closed loops of SUN indices, this object will be suppressed to 1 over n squared in the large n limit with respect to this. And the same is true for any other correction. So there is no generation of counter term to this vertex. And the same is true. The same is true for this. So you will not have generation of mass in the planar limit.
Yeah, but I mean, all the discussion about the double traces that you have to add for, so you consider them done and you are in the fixed point, you mean?
Yes.
Or, okay.
I don't consider it done, because I'm just... those are quantities that affects only very specific quantities. The issue of double traces affects only very specific quantity in the theory, and it's not worth now to go into these details, in my opinion. Okay. Yes, there are small size operators without spin that actually need some renormalization, but that's under control.
Is there any understanding on finite n whether you can make it conformal or
No.
it's impossible? It's known it's not possible, or you don't know?
My intuition is that if n is finite, this thing starts to look a lot like lambda phi 4 theory, because I start to have all those diagrams that I was not considering. Now they do not suppress anymore.
But
So
does that mean gamma deformed, I don't know, n equals 4 is not conformal theory then?
Can you say it again?
that is a very good point, and I don't think that for general gammas there is anywhere written a computation that finds conformal fixed points for general n. I know that there is a paper by Penati, Sant'Ambrogio, and others where it is claimed that this is actually not true, whereas for beta deformation, or at least for real deformation parameters gamma, which is the opposite of what we do in fishnet, where we set them to infinite and imaginary, that it should, in that case, it should exist, the conformal fixed point. But is the opposite regime, in a sense, right? Because having real gammas, it's not connected to the fishnet. Gammas are imaginary, or at least
Wait,
they have an infinite imaginary part.
You can diagrammatically compute the beta function at one loop at least, for example, for the general gamma deformation, and you can see the fixed point there.
At one loop, everything can be done. I would say.
This I agree, okay.
It also at two loops. Already in the papers by Lee and Strassler, you will find solutions. Okay, you can go up to a certain number of loops, and I apologize, I don't remember if it is 5 loops. I think 5 loops where you stop to be able to find the solution for the critical point for generic parameters. But we can discuss this later, and we can go through the literature for that. Okay. So the thing is that we have here this conformal triangle and the action of the B operator. Now the B operator has a kernel once again, has power 1, 1, and here there was a wrapping. Okay, so the power of this propagator, this vertical propagator, is 2, and it is applied by the conformal triangle, and here I will limit myself to the scalar case, the scalar situation. So here it would be 1 minus delta over 2, delta over 2, and delta over 2. And this is a point x naught. Okay? if we put everything together and we make a quick counting of the powers, these are both are cubic vertices, where the sum of the powers of the propagators is equal to d. And so these integrations can be performed by star triangle transformation. And yeah, so in the end, after a few graphical passages, one will obtain the eigenvalue times the same conformal triangle you have started from, with the same powers, delta over 2, and 3 minus delta over 2. Excuse me, is 1 minus delta over 2. Okay? And then we will deal with that eigenvalue. The thing is that, why I want to diagonalize B once again? Because I express the entire perturbative expansion of this n-point function, in this case 4-point function, because j is equal to 2, as a geometric series. So if I express B in a basis, if I expand this object in a basis of the eigenvalues of B, I immediately have a non-perturbative expression for the correlator. Now, in order to expand B in a basis of its eigenfunction, I need to be sure that this basis is in fact a orthogonal basis, and there is an associated completeness relation. Okay, but this is the case for conformal triangles. This is an old topic. So there is a well-known book about it by Dobrev, Mack, and others for reference. But in short, what you can write is a completeness. Okay, so first you have a completeness. So well, you have an orthogonality. Okay, orthogonality. Ay, ay, ay. And I'm doing things in 4D now. Okay. Okay. This orthogonality is not quite an orthogonality. So okay, it has two terms. Okay. Right. So the first line is really what you would say orthogonality, the second line not, but this is because is due to the symmetry with respect to shadow transformation. You see that shadow transformation, which sends delta to dimension minus delta, so to 2 minus I nu is exchanging nu with minus nu, and this is the origin of these two terms. Therefore, the correspondent completeness relation is given by summing only over positive values of nu. Okay, so we are The idea is that we are injecting in the S channel a base of, we are exchanging operators in the S channel that should have a physical scaling dimension. So, right, we will look yes, so we will distinguish basically these two lines as relative to physical operator and shadow operator, and we have to sum only over the physical ones. And this is enough mathematically to have completeness. So the measure in the expansion is, of course, given by only the first line. Okay, so the following orthogonality is true. And the following incompleteness is true. Now, if we insert the completeness inside the formula, we will translate a geometric series of integral operators, since this is a completeness over its eigenfunction, really into an expression. So, and what happens for this 4-point case is that, well, the result is not far away. Okay, it's just one passage. It's going to be this. Delta. Summation over the tensor rank, integration over the principal series parameter, I hope you can still see here. Yeah. Of course, this is not all, in the sense that there is a tree level, right? I have an expression in terms of U and V conformal ratios here, but there is a tree level term. The insertion of this completeness inside the geometric series translates the correlator into a conformal partial wave expansion. This G delta L is the usual term containing conformal blocks, divided by this is what remembers about the geometric series. Okay, so it's essentially what comes from 1 over 1 minus b xi when j is equal to 2. And okay, you see that instead of having 1 minus b, I have eigenvalue to the power minus 1 minus just the coupling, but this is technicality. Is due to the fact that there is a last term of this type that has to be taken into account to complete the graph, a last row. Now you see that there is a straightforward OP interpretation of this formula where you are going to find poles given by the zeros of this denominator and are going to determine the spectrum, so the scaling dimension of the exchanged operator in the S channel as a function of xi for any possible spin, for the possible spins L. And also computing the residue corresponding to these poles, you will immediately have the associated 3-point structure constants in fact, at all orders in the coupling. If you can easily solve the pole equation, and this is the case because this pole equation is really simple one with respect to what you are used to in n equals to 4 and so on, because it is just a polynomial. And the fact that it is a polynomial, it already tells you something quite exotic here, that there is a finite number of exchange operator, okay? And the degree of this polynomial is 4 for 4 dimensions. It would be 2 for 2 dimensions, and then you can go on. But here it comes an interesting part, which probably will take the rest of my lecture. I'm coming to you. Yes?
That finite number of exchange operators, but if you take into account spin, there are
Right.
many.
Right. For every spin, there is a finite number of exchange operator. That it means that there is a truncation with respect to the twist. Okay, there are only 2 twists exchanged here. This is degree 4 polynomial, but this eigenvalue, this is what I called in my formula H delta L minus 1. The eigenvalue of the operator B with j equal to 2 is 1 over this. And right, yes, for every twist there are two physical solutions, because
Yeah, so you can say that it's specific for even dimensions, right? This truncation.
this truncation is specific for even dimension. That's correct. Because if you would repeat the same computation of the eigenvalue by star triangle for odd dimension, a nice simplification of ratio of gammas. So we are speaking, gammas means infinite zeros and infinite poles, because are ratios, right? There is a simplification only at even space-time dimension. But let's stick to this, because this one is, well, first of all, d equal 4 is very interesting. D equal 2 is also very interesting because, for instance, for j equal to 3, the problem would be the same as studied by Simon.
And d equal 1 is SYK. So
well, this is what I wrote in my paper, but it's not really SYK. I mean, it's like a sort of version of connected to SYK. But symmetry-wise, yeah, it's a very related problem. Now, I don't know if one can really identify them 100%. We don't have fermions here. SYK is made with fermions. There is some disorder usually. No, J has there is a coupling with a certain distribution, probabilistic distribution. Okay. Yeah. But you would have to, okay, but you would have to take into account some distribution for the coupling, I guess, or
you just draw this fishnet-like diagram on a disk, and you have a very similar diagrammatic expansion that you can resum in Xi, where Xi now is some average of the SYK coupling.
okay, thanks for the comment. All right. So what happens here? There are two solutions, two physical solutions. You see, if you send delta to 4 minus delta, this guy is invariant. This goes to this, and this goes to this, okay? And vice versa. So you can find solution from this equation of twist 2 and of twist 4 as a function of Xi. There can be some detail added here, right? These two operators have quite different, and L, of course, quite different behavior with respect to the way they're expanding Xi. But I want to point out something different at this point. That is, You see, here is higher twist, but there is only one exchange operator. This is somehow strange, because what could be these operators? Well, for twist 2, recall that this is the 4-point function. The fields are all point split. So 4 fields, 4 point. This is what we are looking at. Okay? So the only thing you can exchange at twist 2 is this object in the theory, because you have to conserve the number of x fields, the total number of x fields. Right? And I would raise the twist. No, yes? Twist, not spin. Right. Now let's raise the twist. And if I raise the twist, I start having mixing, because I have, at this point, as you say, more possibilities to realize this operator. Let me just consider L equal to 0. Okay? Once again, I find only one solution here, but there is not only one. It's not clear what is the operator. Okay, this is the right number of x, because I have 3x and one anti-x, so it's 2. It's okay with the quantum numbers of the external state. But then there are other options. Let me write them here. Let's write the multiplet at twist 4. Multiplet at twist 4 is these 3 operators, and then there is what I already wrote. But this, we can already don't care about it. There is no way that it is interact in a planar fishnet theory with others. You cannot write a graph which is not 3-level that connects to any of them. It would be non-planar. Okay, so the mixing and the operator, this solution, which was computed, for instance, first by Kolya, Grisha, Volodya, and others, should be identified with an operator. Which one of these 3, or which mixture of these 3? And why I have one solution and I don't have three of them? Okay. So the mixing happens, as it usually is in quantum field theory at loop level, but it is due to the non-unitarity of the theory, the chirality of this vertex, is not the usual mixing that you would expect. And here I'm going to go towards my last claim, my conclusion. If I give names to these operators, this is not the right guy. Right. O1. You don't have two x's and box? Two x's and box are related to what I'm writing by the equations of motion. O2. O1 and O3. So you consider the mixing, so the two-point function between the Baire operators, okay, and start writing down Feynman integrals. Okay. The first contribution you get at one loop, it exists for this two-point function, and is the following. Then you could consider also the second case, which would get the first planar contribution These are x and these are y. Red are y. Okay, and y bar. These will appear only at 2 loops, so Xi4, and will look like the following. Okay. And similarly for this transition that will happen, it will have the same type of diagram as upstairs here. The thing is that if I now consider O1 going to O2 dagger, this is 0. O3 going to O2 dagger, this is 0, and the same here. Okay? So these transitions can happen only in one direction, not in the other, and this is an effect of the chirality of the vertex in the planar limit. So what does it mean? That if now you have infinities, and you have to compute, so you have to renormalize your operators. Okay? And you can do it in minimal subtraction, in dimensional regularization. That's what one would do. Okay? To define a renormalized operator. And compute a mixing matrix for the scaling dimensions. This matrix is not going to be diagonalizable because you see its element will be not symmetric. And this will, what does this mean is a signature, well, or rather an operational definition, a practical definition of a logarithmic conformal field theory, where the matrix of anomalous dimension, so when resolving the mixing, can at most make you reorganize the multiplet into Jordan blocks. So you will never get rotating, so finding the rotation that unmixes the renormalized operator. You will never find, say, delta 1 tilde, delta 2 tilde, delta 3 tilde in this mixing of 3 operators. But what you find instead is a block structure of this type. Okay? It's a block structure of this type. So the first 2x2 block is a logarithmic multiplet, is what is called the logarithmic multiplet. And the last block, it is indeed a standard scaling dimension which stands on the diagonal of this matrix. Here we have only one solution for twist 4, and we don't see the operators corresponding to the logarithmic multiplet. But why so? Well, this is not really an answered question, but the intuition is the following. That operators that, you see, this is a raising operator in a spin system. So it's something that it makes your state drift. I mean, if you have a spin system, like you have a system of x's and y's, okay? You start from this state. The only action of this operator, or the higher dimension analog, is to move x's across y's.
Sorry,
Okay.
is this Jordan structure there for at all loops?
Sorry?
Is this structure there at all loops?
Absolutely. Yeah. Because this is a good point. When you have, the point I want to make, in fact, is that structure which is logarithmic is something that tends to stop at a certain number of loops, is limited in the number of loops. Okay, once I exchange, the only thing I can do with my vertex is exchange the position on the initial state of x's and y's, where x go through y's, and I cannot go back due to this chirality, due to this non-unitarity. Okay, so the time evolution is a drifting in this direction. And so after I moved all the x's through the y's, I have to stop. There are no other corrections. And the reason, it's more an idea. Why I don't see why I don't see logarithmic operators in the 4-point function that I'm considering is that you see this 4-point function is organized as a geometric series. So it's somehow the opposite of having something that where you stop having correction after a certain point.
Sorry, I think my question was slightly different. So, you know, you have this Jordan block, but you know, if you go to, like, I'm not sure how this works here, but if you imagine you're normalizing these operators to higher and higher orders, like as soon as you get just diagonal elements as different values, then this Jordan block structure gets broken into a normal, just diagonalizable matrix.
That's true, but
So
here
you have
is
to have this 0 and 0, right? They have to stay exactly equal to each other at all loops. So I'm asking if this is what's happening.
this is a loop. This is, let me look at it again.
You're saying that this is
I can do another transition at 2 loops, and that's it. And then I'm done, because I moved all the x's through the y's.
okay. So you only need to renormalize it first few loops here.
I have to renormalize the first 2 loops, and that's it. So, and this is my conclusive statement. If I want to find what 4-point function with the same external charges I should study in order to describe it, to expand it over logarithmic conformal blocks and really detect the exchange of logarithmic operators, not this double trace object, which doesn't pair to the logarithmic part of the multiplet because it's unfriendly to these drifting effects. I don't really observe. I just have wrappings. On the other end, I would have to consider XX, X bar, point split. Sorry. Sorry, I'm saying something incorrect. I have to consider single trace 4-point function. For instance, this, or in general, this. These single trace 4-point function are completely described will be completely described by the exchange of this part. Now, the rank will change depending on my choice of N and M. Okay? And they receive contribution in the perturbative expansion by indeed one single Feynman diagram at a specific order. It is the case that we can compute them explicitly by separation of variable of the same spin chain by changing the boundary condition. Cylinder, so periodic boundary condition for the double trace correlator, disk, so open boundary condition with the screening charge at infinity and 0 for the disk topology, and these are so-known Basso-Dixon correlator. So thanks for your attention, and also for a little extra time. I guess I was granted, or not, or I have still 10 minutes. Very good. Mm-hmm.
What is the final summary of what state is flowing?
This,
You're discussing some mixing, but then what's the punchline finally? What is the state?
the state that no. Yes. Let me see how can I answer to that. I mean, how precise I can be. Right.
Can you give an example of one that would not truncate? Maybe that's what I'm
There is only one that, yes, okay.
Which one is it? With some pictures?
It will be linear combination. It will be a linear combination of O1, O2, and O3. So when I do this procedure, okay, I will pack the effect of truncation in the first block, and somehow pack together all that does not truncate in the last block.
What's an example of one that is not? How could it not truncate?
Yes. So you should go a little bit at higher order, like 4 loops, for instance. The first thing comes to my mind, or actually 2 loops already. I'll show it here. And also I will show it here. Now you obtain the same state again. And if you right cut, if you cut the Feynman diagram, you can see here such type of state, I guess. Sorry, I cut in wrong place.
No, but I understood. This diagram, as Collier just said, now you can put many red lines going around because there are no red lines in the middle there, right? So
Yes.
now I can put wheels there. So if you compute, so this state, if you compute its 2-point function, you would get then the anomalous dimension exactly that you computed, this delta 4.
Yes. Well, yes. Other finite size correction are present also in the others, right? So it's going to be a linear combination of these states. We have a perturbative computation of what is the basis, what is the exact what is perturbative expression for the 3 basis elements where things are brought in this form.
Okay.
But it's not, I mean, you really have to mix. So mixing happens. It's not that the basis is already one to one.
Mm-hmm. Can you, this correlation function, the way you compute it, of course, it's very OP friendly because you decided to decompose things in conformal blocks from the very beginning, basically, almost conformal blocks. I mean.
Yeah. It's really conformal blocks, and that's why I had to do this explanation. Why in a non-unitary theory I can really use conformal blocks.
Uh-huh. But can you now rewrite the result? Can you do some resummations of this result? Can you write it, for example, in a way that looks like some hexagonalization, for example?
Yes. Yes, if I keep the point split. Not if I start, I mean, if I start to put the points together, I will have divergent Feynman diagrams, and I would prefer not to do. But sure.
For 4-point function, can you write that 4-point function as a bunch of hexagons?
I think you want a non-perturbative answer, and
Yes.
yes, and therefore not, because the hexagonalization I could do would depend on the number of wrapping in the following way. The cuts of the hexagonalization would be along, I will have 2 cuts here, 1 cut here, and 1 cut that goes behind here. This defines a triangulation of a sphere with 4 punctures. But then you see that what flows along across the cuts, which is the number of mirror excitations, depends on the number of wrappings, so on the perturbative order. And this means that the matrix part of the hexagonalization integral will change depending on the perturbative order. So then one would have to deal with that, right? So how can I resum so easily?
No, I'm not saying that. I mean, in the hexagonalization, you would also have sums over how many mirror particles you put and so on.
Right.
But so you say, but it is possible to rewrite that, as a sum of putting particles on edges of hexagons instead of doing the usual OP.
Right, right.
I see.
It is
Do
just
we learn something about this? What are we learning? I mean, we did a lot of computations here, and then we got some ugly expression. What are we learning for n=4 or for CFTs?
Well, one limit where there are two limits where you can resum either at each order in perturbation theory, you can resum this 4-point function into some HPLs, or at strong coupling you also can resum, and then you get this beautiful picture of two fishes and fish chain emerging here. So you can actually like find classical solution which action gives the amplitude for this 4-point function.
And there are also more interesting things, depending from the taste. For instance, I think the most, very interesting quantities, rather than multi-trace correlator, are single-trace correlators in this theory. First, they are almost a pure example of logarithmic CFT, which is a curious topic to study. I think it's not studied a lot. Secondly, we can compute them exactly from hexagonalization. So we can, for instance, provide an example where the hexagonalization of n=4 is derived rigorously from computation of spin chain overlaps. And I'm happy to discuss this later in the day. So starting from a 4-point disk integral, I can consider 5, 6-point disk integral, have a hexagonalization representation, which in terms of a spin chain is literally a representation in a basis of separated variables, and match it with the conjectured limit of n=4 hexagonalization, whereas here it's a direct derivation. Secondly, that is a nice representation to actually compute Feynman diagrams. So going to certain OPE, these SOV integrals, they generally simplifies, and they can practically be evaluated as multiple Mellin integrals. They are simple to, relatively very, very simple. If you take into account that, look, n and m, this is an n times m 4-point, n times n loop 4-point integral, and you can compute it exactly. If you go to 5-point or 6-point, maybe you don't compute it exactly, but in AOP, it's easy to expand for any loop that you want. Of course, it's a specific topology. But you are producing a lot of data that people that are studying the space of functions for amplitudes will use first. Second, there is another property of fishnet integral that I just mentioned quickly, that for point split disk integral, you can prove Youngian symmetry. So this is another aspect of Bootstrap. There is an algebra of non-local conserved charges that constrain a lot the result on your integral and eventually can actually fix it. So if you start to put together Youngian symmetry, which is a consequence of star triangle relation in a sense, the separation of variable representation, which is also a consequence of integrability, you start to have really a lot of information and describe the basis of multi-loop, multi-point Feynman integrals that will give you an intuition, since here Feynman integrals and correlators are actually the same thing, will give you an intuition, a better intuition on which functions describe multi-loop, multi-point correlators or amplitudes. And I think this can be a very useful application of this computation. If you consider, for instance, 6-point double box, this is already this 6-point fishnet is already not an easy object to compute. You will find maybe in some papers some very complicated expression in terms of elliptic polylogs, but how does it evaluate? For instance, when I put these 2 points and these 2 points together, with this formalism you can compute it efficiently. And what else? Yeah, I don't know.
Can I ask if you can introduce some equivalence relation on the space of operators which would remove these Jordan cells? Some kind of filtration, for example, operators where there are more axes to the left and to the right, you just put them to 0. This subspace will be invariant on the renormal flow, and if you factorize over it, you get diagonalized LCD simple on normal flow.
Exactly. I think so. It's not a rigorous answer because, well, you would like a formal, rigorous procedure to do this, but this is an example where this is what is going on. So, of course, practically the thing is that these operators are there. When you have to sum for your completeness, they should be there. They are local operator of the theory. But in practice, the 3-point structure constant must be 0 with the external states. More ideologically, say, is the fact that something that is expressed as a geometric series of all identical repeating contributions, to me, is very unfriendly to something where I'm just moving fields x over across fields y, and then I stop. Right, so I think this is, for instance, a way to filtrate them away, even for higher length, higher twist of the operator.
So just one comment in principle, you can still consider the separators, but within n equals 4, but consider a more tender limit, you know, which wouldn't kill those dimensions, and then they will be lifted up, and that's what Amit and Liang studied, right? I don't know if they published though, but...
Amit and De Liang or Gwenel? De Liang may be able to confirm.
Yeah, can you confirm, please?
Where is it?
All right, maybe I withdraw the statement if it's not confirmed.
Yeah, there are other possible deformations, that's true. This is very mean.
Okay, let's thank Enrico.